So an Apple Maps user walks into a bar, or it could have been a lake or a school. All right, so I am Kevin Bell, work with Salt Lake City in the IT department, and was with the transportation division for a number of years and have been able to do a lot of really interesting work there, a lot of fun. Let me just do this. This is where we're at right here, looking at the sunshed for the entire county. It's big data, a lot of information here. And I kind of wanted to go through how this is generated. Some of you have probably seen this dog and pony show before, so you might just want to get up and leave now if you have. But it's a big data problem, and that's what I wanted to show you. Let me just close that and open this. Let's see. Pull this up and start this. Okay, so I actually photoshopped the CPU lines here to make them stand out a little bit, but I've got a 32-core server with 100 gigs of RAM, and it ran at 80% capacity for over a month to compute the sunshed for the entire city. So you're essentially talking about tracing sunlight moving through the sky over a billion data points. And so that's what I'm going to show you is how this worked. So parallel processes. If you ever saw a big column of smoke downtown, it was probably this server. So everybody here is probably semi-familiar with LiDAR, but if you're not, it's like radar. It's taking measurements from lasers instead of from radio waves. Essentially, a plane flies over the area, scanning with a laser and measuring the time it takes back for the laser to come back, and you get these huge data sets. The plane has an inertial measurement unit on it, and it's all high-tech GPS in order to essentially just get a really big list of X, Y, Z values. This is what the data looks like if you pull up the raw data from AGRC at the highest resolution. We only have the raw data text file. So yeah, for Salt Lake County, it's about 5 billion points. And if you throw these elevations or this text file more or less just straight into ARC-scene, it looks something like this. It's just this random cloud of points. But if you start zooming back, and now we're looking at a chunk of the avenues. Let me go back here. So you've got this random scatter of points. So in order to process this and be able to feed this into some of the GIS tools, we have to do a lot of processing for this. And the reason why this whole project came about was there was an agenda to make a solar website for Salt Lake City. And the initial plan was just to make a pin map that said, well, here's a solar installation. And I heard about that. And from our sustainability director, mentioned this to me, and I was like, well, maybe we can spice it up a little bit more. Rather than just doing a pin map, I've got something that I'd like to show you. And so we actually, our first LiDAR data set that Salt Lake City received was for the 2002 Olympics. And so I started playing around with that. I had my own software at home, and I have a little micro farm, little hobby farm that's a half acre over in Glendale. And so I started using ArcObjects and VBA and started writing my own routines to do sunlight modeling. And it was essentially generating contours based off of this LiDAR for like the number of hours of sunlight a day over the course of the year. And this was before we had the really amazing tools in ArcGIS Spatial Analyst. That's what I'm using now. But initially it was just doing this on my own. And so it's really neat though. I showed our sustainability director what I was doing at my own house and said that, yeah, we can pretty much get a better idea of the solar potential for any location based on this LiDAR data. And she stopped the meeting and we walked right into the mayor's office and she said, Ralph, look at this. And we were looking at real solar, products that were available for just my yard. But mayor said, well, can you do this for the whole city? And I said, well, I can try. And I soon found out that it was kind of a trick. So anyway, normally with a lot of data sets, you can just kind of divide and conquer. Tile the data up, solve the problem for that area, and then move on to the next tile, solve that. And that's what I did. So for my test area, and it came out looking like Argyle socks. Apparently what happens is you get, if your area of interest has shadows being cast into it that you're not accounting for, then you have problems. You're getting bad data around the entire perimeter of your area of interest that you're solving for. And so I developed a Python library that essentially is a moving window, variably buffered type of algorithm, and that's what I'm going to show you. But so in order to start, we just take these XYZ points, this random point cloud, and we have to normalize it into the grids that we all love so much. If you throw all of this stuff in there, you've got up to like 6 points in a given square meter. And they could be the top of the tree, the middle of the tree, halfway down the tree, and then the ground. And so this code is on the old GIS site to flesh out first and last returns from the raw point cloud data. And it's actually really simple. I mean, yeah, you could pay good money to pay a vendor to make these different return products off raw LiDAR, but you don't really need to. It's really, really simple. And this is how it works in the Python script that does this. You essentially have all these XYZs, right? And they've got the, maybe 6 decimal points on them. So you might have a point right on the top of my head. You might have a point right over here, one up there a little bit, one on the ground right beneath me. And what I did was I was like, well, how am I going to get this data out and actually make it more usable into a normalized grid? And so what I did was I just looped through the text file in Python, nothing to do with GIS yet. Just Python has a function for reading text files, and it's really fast. So as I read each line, I pulled in the latitude and the longitude, dropped the decimal points, concatenated them together, and made those a key in a dictionary. And then for every time that unique XY came up again, I appended the Z value to a list. Sort the Z value. Now you've got, for every XY pair, you've got either the first return or the last return. And so then you just split your concatenated XY back out, and you've got a very clean file that you can work with and then put into a normal grid like this that's relatively clean. The code looks crazy if you go look at the site, but if you read through it, understanding the basic data structures in Python, if you understand those, then it's really quite a simple script, although it looks like hieroglyphics. It's, you just get in there and it's really a simple deal. But so here's the library, and it's color-coded for height. And you can see subtle transitions. You can see the crown of the road. This information is so detailed. But so then we extrude it into a real 3D model and stuff to kind of get an idea of what we're working with. This is first return data, so it looks like blankets have been thrown over the trees and things. It's really 2D and a half. But then we simulate the sun moving through the sky, and it's just like that. So my end of it is not so much the solar modeling, it's how do I feed so much data through the spatial analyst solar radiation tool. I like this slide because this is what your computer is going to look like if you go about this the wrong way. And I found that out the hard way a few times. But so this is where we get into that, how you do how you solve tile by tile without introducing errors that would normally be inherent in a normal divide and conquer strategy. So what I do is I divide the city up into small chunks. This is probably 1,000 feet by 1,000 feet. I recently just did this for the entire county and was using a larger area of interest because we've got 64-bit processing now, and so I could use more RAM. But in this case, I was doing 1,000 feet by 1,000 feet, and so for each tile, let me turn off my phone here. For each tile, I figure out, just with some basic commands, what the minimum and maximum elevation is in that tile. And so now we're color coding these tiles according to their maximum elevation. And so from there, we go look around and we find for this tile in the center, we find the tile next to it that has the largest elevation. So I'm calling that the adjacent maximum here. And it's pretty simple to do that. You're using essentially a point distance command and generated a table, and actually the point distance table is then looped over with Python to actually extract and find the highest location. And then from there, we look at the lowest point in our solve cell and compare it to the largest, to the adjacent max, to get the delta Z between our adjacent tile and this one. So in this case, we're looking at 147 meters. This is probably downtown or something. So given the delta Z and a monthly sun angle, we're then able to use a little bit of trig to find a buffer distance. And so everybody's with me so far, right? So the whole idea here is that we're going to solve for the entire buffer and then clip it back. And that accounts for the entire area of interest, including the shadows cast from outside. But the whole concept here is that we're doing it like this per month because these things take time to solve. One of these tiles can take 10 minutes to solve, and we're doing that for a large area, so that's where the whole month of processing comes in on multiple cores. And so the whole concept is to not process any more data than we have to in order to do this. So this tile down lower here doesn't have a lot of large objects surrounding it, so the buffer distance is small, whereas this other one up in the upper part of the screen takes a larger buffer. It's probably downtown and has some larger area that we need to account for. So now we're looking at these tiles color-coded according to the size of the buffer that is going to be necessary in order to correctly solve these things. And you see downtown, it's red, lot bigger buffers down there. But out at the airport, it's blue, very little buffers required at all. I can almost solve, just one tile and maybe a foot around it. There's nothing to cast a shadow into that area. But there's this area right up on the north end of the airport, and it's red. And when we saw that, we were going, hey, what's going on with that? And I was like, oh, it's the air traffic control tower. So pretty cool stuff. Kind of geeky. But so what we do is we clip the LiDAR out. So the solar area tool will take any surface and compute things like the photovoltaic potential in watt-hours per square meter, or also the direct hours of sunlight. And so we feed this surface to it by clipping out the tile of interest as well as the entire buffer, and then solve the solar for that area, and then delete the buffer. And now we've got seamless, flawless surface that is actually accounting for the area around it. So the way that just pulling some of these, the way that this algorithm really works, and this would just be for 1 month, but we're looking at the buffer for January and February, March, April, May, June, July, August, September, October, November, December, and then the next one, now we've got larger buffers, just January, February, March, April, May, like this. So this is what this thing's doing, as it moves through, and then we've got all these tiles. All we've got to do is mosaic them together into one large data set, and we're good to go. So for the county, it's essentially 1 billion data points with 24 attributes that include monthly values for that meter's watt-hour per square meter, as well as that meter's number of hours of direct sunlight. So you can click anywhere in the valley and say this area gets 8 hours of sunlight in January. So it supports photovoltaic analysis as well as direct gain systems like air heat and water heat. I've got a retrofit trommel inside of my house that heats the air. It's essentially a glass door, a little glass box that's there, and the air is heated and rises into the house. The air in the house stratifies and sinks, and the coldest air in the house returns to the collector, and it thermosiphons all day long. It's kind of neat. So you could also use it for xeriscaping or garden design, things like that. So we come full circle to that. But speaking of full circle, those 24 billion data points, the 24 attributes on each point, if you stack pennies up 24 billion times, that's enough to wrap around the entire Earth. So kind of fun stuff there. So we have data for, and actually I need to update these slides, but we've got data for the whole county at this point. And I set this PowerPoint up so I wouldn't have to be online or have ArcMap or anything. But this is what you get as far as the look. You can see the hot red sides of the buildings and things and the cool shadows. So we have direct hours of sunlight. So at the tip of that yellow arrow, we're looking at how much direct sunlight we're getting per month, and kind of animating over the course of the year. And then we also have the direct radiation in terms of watt hours per square meter. So here we're looking at kilowatt hours per square meter. So it's just kind of fun to look at, I think. And then Bert Granberg up at AGRC, AGRC was a huge partner in this. I did all the generating all of the rasters in order to do this. And naively, I thought, well, we'd just make some geoprocessing routine that would query that raster and done. We'll aggregate this data, feed it back to the website, and give people a report. Well, Bert started playing around with this and figured out really quickly that the nature of rasters, it's a line scan type of thing, and it's not very queryable in an efficient way with such a large data set. So he determined that it was necessary to convert all of these 24 different rasters into a single point feature with those 24 attributes, rather than having 24 rasters to read through. Monthly values per energy type, direct sunlight or kilowatt hours. And so he wrote this VBA code that was brilliant, and it ripped through all these 24 values and then spit out these points. And I've recently just rewrote that in Python just because VBA is kind of going out of style. But I wanted to show anybody that's interested in raster data. There's this really cool function right here, arcpy raster to numpy array. So what this function is doing is essentially converting any raster into just an array, a mathematical array. You've got the XY coordinate with whatever values there. And by jumping out to pulling this into a numpy array, numerical Python array, the processing went really, really fast compared to normal commands that are out of the box. So essentially what this does is it just goes through and reads through row by row and column by column and pulls all of that information into memory. And then once all of the information is in memory, then we generate a point for that location and write each of the monthly attributes to that point. And I won't torture you with going through this line by line or anything. But that's generally how it works. So let's see here. So that was, so we've got has anybody seen the Salt Lake City Solar website? Raise your hands. Not very many people. Okay, some. Well, so when you go to the portal, it looks like this. You've got a pin map with commercial installations, solar installations in green, and blue ones are residential. So it's just kind of a pin the tail on the donkey kind of map at one level. But you zoom in and you draw an area across one of the buildings, and you get this graph back that shows you how many watt hours of electricity you could generate. The graph here isn't perfectly smooth because there's different days. Some days have 31 days, or some months have 31 days, some have less. But you also get this report that says the total selected roof area. There's a slider, so you could dial that back, a ways. And then this is saying that this area you could put a 29 kilowatt system in, generating 35,000 kilowatt hours, saving $2,000 a year, and estimating CO2 savings of 44 pounds a year. Yeah, 44 pounds a year. So kind of fun. It's also you've got estimations on the size of the system that you could put up and things like that. So it's just kind of fun to play around on. This is just some of the, you don't need all this. I was kind of messing that up. But so it doesn't really end there. I did all the data processing, and if Steve could come up, Steve's around, to actually make that website work. Steve did a bunch of magic. He's the web developer guy that does stuff that I can't comprehend, and so I wanted him to explain kind of what goes on under the hood to make that work. And I will turn it over to him, and we'll take questions after Steve's done.
Okay, so AGRC's role in the solar mapping project was mainly a service provider. So as you've heard throughout the presentations, we offer base maps. And it's really easy for people to use them. It's one line of code. The images that Kevin was just showing were of an old base map, and in the matter of 5 minutes, we updated to one that we maintain. So that's great. He showed this. We host these base maps as well, so they're coming off of our servers. The solar website also has the geocoding ability. So they're sending in the address. We send back some JSON with the XY and some other values, and then subsequently they can put a point on a map. So the solar analysis process is you draw a shape, you simplify the shape, you submit it for analysis, you get some information, and you display the results. So simplifying that point, or that polygon that Kevin was just showing, would come in something like this, and that's how it's represented in JSON. And we simplify that because depending on the order that the points are input represents positive and negative space, so you want to have that be and you don't want like self-intersecting polygons and stuff like that. So we offer a geometry service that simplifies geometries. They're taking advantage of that. And then for some reason they end up sending us latitude, longitude. We convert that back to NAT83, and then we build a geometry from that. We query those solar data points via that ArcObject script that turned it into a point feature class. They're spaced 1 meter apart. They have the 12 attributes that Kevin mentioned. And then we aggregate the results. So this is kind of how it looks like. This negative white space is like a cul-de-sac. The highlighted blue is like a parcel. These points are the solar values. The red line would be your digitized shape in the web map, and then our process goes through, queries, does like a spatial query, grabs all those points, and then aggregates all the monthly values. Each point has these solar monthly values as well as some other things I'm not too sure about.
Those are the direct duration of that, like sunlight hours. That shows how many hours of sunlight.
Okay, so these are annual values of sunlight and intensity. Anyway, after we do that spatial query and the aggregation, we return an array that is the average of the direct sunlight hours per month, and then the sum, I believe, of the radiation intensity. And then that's what they use to build those graphs, the Google charts. So that was basically our role in this as a service provider. They told us what they needed, and we put together some services that allowed them to quickly put up that website.
If anybody has any questions, you're welcome to ask them. I'll just show you this. So we've got, let's see, how do we do this? So we're looking at upgrading the website to include the rest of the county. We're going to have it done by February. Right now we're actually renovating the entire website's design. If you just do a Google search for Salt Lake City Solar, it'll come right up. It's kind of a fun project. It's big data. The resulting database was about 170 gigabytes. Kind of amazing though that it was reduced after compressing it, just doing the normal command to compress the file geodatabase. It went from like 170 gigabytes down to like 40 gigabytes. So amazing thing there. So, yeah. All right. Well, if there's
Can you track how much traffic you have on that website? Do you have any analytics?
Yes, we were getting about 200 unique visitors a day for a couple of months when we were looking at it last. So there is a lot of interest, and we've had a lot of people calling. This is done in partnership with Utah Clean Energy and the state and the county. I had Mark and his team at the county actually do a lot of the pre-processing for me with that script that I was mentioning that cleans up the point data. I just, it was a county project, so I, put them to work on some of it, and they did a great job filtering out some of the noise and things like that. So big thanks to the, county contribution as well as the state. And really, a lot of the content on this website is coming directly from Utah Clean Energy. So they've got a really big agenda to make solar energy available to residents that normally might not know exactly where to get all of this information. So kudos to Utah Clean Energy as well. They've done a lot of work on this. Any others?
Any kind of weather patterns, like cloud cover or average?
The question was, is there any account for weather patterns? And yes, we account for a 30-year average of atmospheric transmissivity as well as the diffuse proportion of light. So it should be a pretty accurate model. But yeah, as you see, we're accounting for the shadows cast off your doghouse. I mean, it's anything that's bigger than a meter is fair game. And the thing is, this isn't really relevant for certain areas like the top of Walmart or some huge big box store. That there's other tools out there like PV watts that will give you a really good assessment for things like that. But where it is important is in locations where you have this tree canopy, in urban settings, in residential settings, you've got this tree canopy that makes one home probably pretty good, and the next one, not so much. Also for the downtown area, here's a building that I really like to look at right here. This one, if you look at it, actually this is the sunshed for March. And if you look at it for January, half this building right here is in full sun and the other half is really shaded. So it's relevant in areas where you've got large buildings that are casting shadows, and residential areas where there's a lot of shadows cast from trees and it might not be so certain. So, go
Have
ahead.
you ever, just for fun, calculated the energy potential of the entire county?
No. So the question was, have I ever calculated the energy potential for the entire county? The interesting thing there is that we have building footprints for Salt Lake City. So it wouldn't be hard to actually, compute the solar potential for the entire city based on those building footprints, because we could filter out a lot of the dead space that you might not want to put solar panels. So yeah, it's an interesting thing. There was another product that I was wanting to get out at some point. And I'm not sure exactly what I do with it. I've got a let's see here. Kind of scrambled all my icons up here. I've got a product that I am working to get out that it's kind of hard to see, but what you're looking at here is I've got a geoprocessing service that will actually go and grab the information and generate solar contours. Right, I'm trying to open this thing up. This is a smart PDF, and this was generated from ArcMap, and it doesn't work real well. It's there it goes. Okay, so right now I've got a 1-foot grid and a 10-foot grid on here. So there's a 10-foot grid, and there's a 1-foot grid on top of there. Let me just zoom in on this. The whole concept here was to enable people to do planning for their own home, for xeriscaping or whatever they might want to do. But actually, it shows them month by month how many hours of sunlight fall on their yard. But this, I'm not real happy with the way that this PDF is working. It's like not very responsive. Okay, there you start to see the solar contours, but it's, you know, it's just kind of choking. This PDF's corrupt, I think. So anyway, in the future, you should be able to click on your house and have a 12-page solar contour map book emailed back to you. It takes about 3 minutes on my screaming desktop machine to interpolate the contour lines. You know, so with that being the case, you know, it'll be a product that will have to be returned to you via email. So anyway, I turned the grid off, but it's still thinking about it, I guess. So, all right, who's going to go out and buy solar panels now? Okay. All right. Well, if there's no more questions, thank you very much.